Okay, so now I want to talk about another classification scheme for stars that gives us more information about them. We talked about the OBA, FG, KM, stellar spectral type classification scheme. All that tells you is which ones are dim and which ones are, well, which ones are hot and blue, the O and B, and which ones are cool and red, the K and M, and everywhere in between. But we can learn more from looking at the brightness and the colors of stars. And by plotting their properties on a graph and looking for patterns. This process and what results from it, which is called the HR diagram, is a super important thing in the history of astronomy. And it's so important that I like to give two analogies first to help get a clearer picture of what's going on. One of the analogies I like to use is to look at athletes, specifically football players. And the reason I choose football is because I think it's the sport in which there's the most variation between players. Look at these two guys. They both play the same sport on the same team. Right? One of them looks to be about 5'7", 190, and the other one looks to be about 6'4", maybe 260. So they give us a good spread of data to ask this question. Suppose we plotted the properties, the physical properties of football players on a graph. Is there a deduction we could make about the different types of football players there are? Okay. Here is data, actual real data about real NFL players. Sports nowadays are very statistics heavy. You can look up on the NFL website the physical characteristics of every player in the league. So these are old, but they wouldn't be any different today in general. And these are just offensive players. If you don't know much about football, that's okay. I'll try to explain the how this relates to the game as we go along. But also, I'll give another example that has nothing to do with football in a minute. What do we see when we look at this graph? First of all, what have we graphed? We have graphed two quantities against one another. On the horizontal axis, we have the weight of each player from looks to be about 160 or so up to more than 350 pounds on the horizontal axis. And on the vertical axis, we've graphed that player's height. So every dot on this graph is a player, and what's graphed is their height and weight. So their height goes all the way down to this person here is less than 5'6". This person here is 6'8.5". So we've graphed all their properties. And what do we see when we look at the graph? If we squint, the first thing we see is the graph goes like this, right? It goes from lower left to top right, which makes perfect sense, right? The overall pattern is that bigger people tend to weigh a few pounds more. So the general slope of the graph is upwards, right? The players that are taller typically have a higher weight. But we also look at the graph and we see clumps. Here's a big clump here. Here's a big clump here. Here's a clump down here that is separate from the clump here. Now, what do the colors and shapes mean? The colors and shapes are the position that the player plays on a football team. Even if we didn't know anything about football, though, we could look at this clump of 300-pound, 6'4" players and guess that they do something fundamentally different than this 5'6", 170-pound player, right? They, on the graph, make a clump that differentiates them from the other players. Likewise, this clump right here, we can see has a different set of physical characteristics from these players down here. Now, why is that? If you know anything about football, you might guess which of these clumps are which. In other words, which positions are in which of these clumps. Who are the players up here in this clump of 300+ pound, 6'2+ individuals? They are offensive linesmen, centers are the green circles, and guards. So these are the guys whose job it is to be just a brick wall between the opposing defense and the quarterback. What is your job if you're an offensive lineman? Is just to be immovable. So what kinds of players are they? They are 320 pounds, 6'4" players. What is this clump down here of players that are generally smaller? And for their weight, they are generally lighter. Those are running backs. What is your job if you're a running back? Your job is to be handed the ball and to run as fast as possible. What physical characteristics do you need to be a good running back? Generally, you need to be agile and fast, and that tends to favor smaller, lighter players. Quarterbacks are mostly up here. They have to be mobile, but also generally tall. Nowadays, quarterbacks are getting taller and taller. Wide receivers are the yellow squares. What is your job if you're a wide receiver? Your job is to run downfield as fast as possible to get to some place where you can catch the ball. And then once you catch the ball, to run some more. So wide receivers, again, tend to be smaller, faster, more agile, but a little taller than the running backs. Why? Because it doesn't matter how tall a running back is. It doesn't matter how tall a wide receiver is, because the higher you can reach above the defender, the better chance you have of catching the ball. So even if we didn't know anything about the game of American gridiron football, and I should be careful when I teach this class that there are sometimes Europeans in the class and students from other places for whom football means something different. Even if you know nothing about American football, you could look at this graph and say there are clearly different kinds of football players who do different things. The graph, by the way, looks exactly, well, it looks similar for if you look at defensive players. You get a clump of big, heavy players and a clump of smaller, lighter, shorter players that are more agile. Who are the shorter, lighter players on the defense? They are players like cornerbacks. Okay, your job is to keep pace with the wide receiver and try to intercept the ball or try to keep him from catching the ball. Safeties, whose job it is to, again, chase down running backs and chase down wide receivers. So you can see the smaller, more agile players up here, the bigger players up here, defensive ends, defensive tackles, people whose job it is to push their way through that offensive line and try to get to the opposing quarterback. So we can see that just looking at a graph of two properties graphed against one another, we can draw some conclusions about the different types of individual groups that might exist within that larger population. Okay, here's a non-football related example. Well, first of all, let's focus on the two things we learned. One simple fact, one more subtle fact. The simple fact is that bigger people tend to weigh more, right? Taller people tend to weigh more. So there's an overall upwards pattern to the graph. And then within that pattern, there are clumps that tell us that there are different groupings within that general pattern. Okay. Let's do the same thing with cars. Okay, we all know how cars work. We all know that there are different sizes of cars. There are little tiny, Kias and Coopers and little Fiats. And there are great big SUVs and such. I've taken a similar graph and I've chosen two quantities to plot on the graph. On the horizontal axis, just like with the football players, is the weight of the vehicle. And this is a graph I made myself. I went to 1999's consumer vehicle safety, whatever website, and I just took all the data of all the cars that were made that year. And the vertical axis is the horsepower of the engine. And we plot these two quantities on the graph. Each dot represents a car. What do we see when we do this? What we see is that there's a general upward trend to the data. If we look at this data here, it slopes up, just like the football player graph slopes up. Why does it slope up? It slopes up because the bigger car you have, the bigger engine you need with more horsepower to get it up to 60 miles an hour so you can drive on the highway. Bigger cars, heavier cars tend to have more powerful engines. They have to. All the cars on the road have to be able to go from 0 to 60 in some reasonable amount of time so you can drive on the highway. So a little tiny car, a little Kia, a little Fiat, a little Cooper Mini, might only weigh 1,600 pounds, and it only needs a 90 horsepower engine. Whereas a big Lincoln Navigator or GMC Armada, some huge SUV, might weigh 4,000 pounds, and it needs a 200 horsepower engine just to get itself up to highway speeds in a reasonable amount of time. This crazy car out here weighs more than 6,000 pounds, and it needs a 300 horsepower engine to get it up to speed. By the way, that's a Hummer H2 is what that dot is. So you can see that there's a group of cars that define this line that goes from little tiny cars with little tiny engines to great big cars with great big powerful engines. And that would define a kind of main grouping of cars. But we also see these other groups of cars that are different, that are set apart from the main trend of the graph. There's this group here, there's this group here, and then there are these two cars up here that make a group. Notice within each group, the group still slopes upwards. Right? It's still true that the heavier your car is, the greater horsepower engine you need. How would we describe how these clumps of cars are different from these cars? First of all, there's fewer of them, so they're rarer. Second of all, what we would say is for a given weight, say 3,000 pounds, these cars have a bigger engine than you would expect them to have, a more powerful engine than you would expect them to have for that weight. These cars have a way bigger engine than you would expect them to have, and these cars have a way, way bigger engine than you would expect them to have. What kinds of cars are these? Think about it for a minute, and I think you can probably guess. These cars in the bottom grouping are just your regular day-to-day drive them to work commuting cars. They are your Nissan Sentras, Toyota Corollas, Ford Focuses, just regular old two-door and four-door sedans. Up at this end, they're SUVs and things like that. What are these cars then? These cars are cars that, for reasons mostly of entertainment, have a bigger car engine than they need to have. These would be your Corvettes. They don't even make the Dodge Viper anymore. That tells you how old this PowerPoint is. Your Dodge Challenger Hellcats or whatever. These are your cars that are built with a bigger engine than they need to have so they can accelerate really, really fast. What is above that? Well, what are those? What is this next group of cars? These are cars that have about the same weight, but even more horsepower than that. These are your high performance cars like Ferraris and Lamborghinis and Maseratis and stuff like that. What are these up here then that have twice as much horsepower as even a Lamborghini or a Ferrari? One of them is super light. It only weighs 1,500 pounds. The other one weighs as much as a normal car. This dot here is an Indy car. And this dot here is like a NASCAR racing car. So these are cars that are built not to drive to work on the highway at 60 miles an hour. These are cars that are built to drive as fast as possible in a little circle. So they're different, and you can tell they're different just by looking at the graph. We wouldn't have to know that car racing existed to look at this graph and say, these cars are different. There's something different about them that sets them apart from these other cars. Okay? That is what we can learn from making a graph like this. Now let's do it with stars. We look at stars, we see two quantities that vary. One is their temperature or their color. The other is their brightness or their luminosity, how much light they really give off. And we look at thousands of stars, and we measure these properties, and we put them on a graph. The way this is usually done, traditionally, when you see this diagram, is luminosity goes in the vertical axis. So dim is at the bottom, bright is at the top. Temperature is backwards on the horizontal axis. So the horizontal axis usually goes from hot to cool. Okay? Hot blue on the left side of the diagram, cool red on the right side of the diagram. So you can think of that as the spectral type, O, B, A, F, G, K, M on the horizontal axis. When we do this, we find that O-type stars are hot and usually also bright. And M-type stars are cool and also usually dim. So the graph looks something like, if we take every star in the sky and put it on the graph, okay, a cool red star would go here. It's dim. A star like the sun that is kind of medium temperature and medium brightness would go here. This hot blue star is bright and has a high temperature, so it goes here. And we plot all the stars in our galaxy in a diagram, and we find that there is a relationship, a standard relationship between brightness and luminosity. Sorry, I used the same word twice. A relationship between temperature and luminosity. The hot stars tend to be bright, cool stars tend to be dim. That makes sense. Just like big cars tend to have big engines. Right? The hotter they are, the more light they give off. That defines the main pattern of the graph, which we call the main sequence of stars. But there are also these other groups that are set apart from the main sequence. And those properties of those groups tell us something about those other types of stars. Okay. This diagram, this graph, is called the Hertzsprung-Russel Diagram. It's important enough that I've never given an astronomy exam where I didn't say, draw and label this picture of the HR diagram. Label where the main sequence are, label where the red giants are, and so on. So this is something you should know, memorize, be able to draw yourself. Okay? Draw what the axes are, hot to cold, dim to bright, draw the shape of the main sequence, and then know where these other groupings are. So I just said a few times, we call this main band of stars that occupies the bulk of the HR diagram and 90% of the stars in the sky, the main sequence. These are your regular old stars just living their lives, burning hydrogen into helium for as long as they can. The sun is a main sequence star located right about here on the HR diagram. Okay, so the HR diagram is not a picture, it's not a map, it is a graph of the properties of stars. But then you got these guys. What's going on here? How do we describe these stars? For a given temperature, they are orange and red, so they are cooler, but they're much brighter than we would expect them to be. Just like the Corvettes and such had a bigger engine than we would expect them to have. So there's something different about them. What's different about them? How do we describe it? Well, how could a cool star be bright? What other thing about it could make it give off more light? If you think about it for a minute, just think about a blue light and a red light. Blue lights usually seem brighter to us than a red light. How would you make the red light brighter? We just make it bigger. Just make a great big giant red light. So our guess for the property that makes these cool stars brighter than we would expect them to be is that they're really, really big in size and physical size. These stars are yellow and blue, but they are also way brighter than we would expect them to be given the normal clump of star properties. So we make the deduction that these stars are big. And we call these groups of stars giants or supergiants. This group here are red giants. This group here are the blue supergiants. What about these stars? How would we describe them? They're hot. They have a high temperature. They give off bluish white light. But they're very, very dim. Why would something hot be very, very dim? Well, the opposite deduction is that they're very, very hot, but they're also very, very small. So this group of stars down here in the lower left of the HR diagram are stars that are hot and blue, but tiny. And we call these stars white dwarfs. So our classification scheme looks something like this. The main sequence occupies the bulk of the HR diagram, from hot, bright stars down to cool, dim stars. Above that are your red giants and your blue giants and blue supergiants. And down in the lower corner are your white dwarfs. So we've deduced the existence of different types of stars with different types of properties through no other means but making a graph and identifying the clumps and figuring out what would the properties of these clumps have to be. We can't look at a red giant in a telescope and see that it's bigger than a main sequence star. Stars are too far away and too small. They look like little specks no matter how powerful our telescope is. The way we know that there are giant stars is that we know there are stars that are brighter than they should be at a given temperature, which must mean they have a big surface area to give off all that light. We know that there are dwarf stars because we know that there are stars that are very, very hot, but nonetheless very, very dim, much dimmer than they should be if they were a regular old O or B main sequence star. Okay. Do I have a picture of a real HR diagram? Maybe I don't. I'll show one in the next video. The next question to ask is, what does this mean? Does it mean that there are just some stars that are giant stars and they're born as giants and that's just what they are? And there's some stars that are dwarf stars and they're just born as dwarfs and that's what they are? Or does it mean that stars change over time from one type to another? That's not what it means in our other graphs, right? Your Chevy Bolt will never grow up into a Chevy Corvette if you wait long enough. It would be nice, but it doesn't happen. A 5'6", 180-pound running back will not grow up into a 6'4", 320-pound linebacker. They're just different, and they stay different. But we don't think that's true of stars. We think that these giant phases and these dwarf phases used to be main sequence stars, and they changed somehow over the course of their lifetime. And the question we will ask ourselves is, what is the evidence for that, and why would that happen? Why would a star go from being a main sequence star to some other kind of star? Why would a star all of a sudden get really, really big? How is that possible? That's where we're headed next.